Very good morning to all of you. In the previous lecture, we have given the meaningful name to infinite series, and we have talked about when we will say a given series converges or diverges, and also we have seen some of the comparison tests there. So now we are in position to define the limit of a function, by which we mean we have been given with a real valued function defined on the set A, whose range is in R. Then we want to decide when the following, that limit x to c f of x will exist. And we will also look at what is that meaning geometrically. Right. So before going to give this the meaningful name to this, we are going to first define the cluster point of a set. So we have been given with a set A, which is a subset of R. Then we say a point C in R is a cluster point of A. If for every delta positive, there exists at least one point of A other than C, such that mod x minus c is less than delta. So if you open up this mod x minus c less than delta, that means that x lies here. X belongs to c minus delta to c plus delta, and which is nothing but the delta neighborhood of c. If you recall, that is nothing but the set of all points which are lies in the delta neighborhood of C. So if you want to write the above definition in terms of neighborhoods, that is as follows. So you, for every delta positive, there exists at least one point of A other than C satisfying this. So if you rewrite this in terms of delta, means every delta neighborhood of C. So every delta neighborhood of C contains at least one point of A other than. So this is what the meaning of this last line, that if for every delta positive there exists at least one point X in A, X not equals to C, such that this happens. So this explicitly tells you that every delta neighborhood of C contains at least one point of A other than. And if you want to write the mathematical form, it is going to be like this. So V delta of C, which is the delta neighborhood of C, intersection with A, and you difference with the singleton set C. This set remains non-empty for every delta positive. Then you say C is a cluster point of A. Now, once we have this definition, we can have more properties attached with the cluster point. Okay, so this is true for every delta positive. So if you choose delta to be 1 by n, so this certainly remains true. Then what will happen? So let's discuss this now. Okay, now let C be a cluster point of A. Then certainly for every delta, the delta neighborhood of C contains at least one point of A other than C. So we choose delta is equals to 1 by n for n where n belongs to natural number. Okay, where n belongs to natural number. Then from the above definition, the following set remains non-empty. So we choose n point xn from this following set. Certainly xn not equals to C because of the definition of the set. For every n belongs to n natural number. Okay. Now, not only that, moreover, xn belongs to this neighborhood of C with radius 1 by n. So certainly xn will satisfy the following. mod xn minus c is strictly less than 1 by n for every n belongs to natural number, which tells you by comparison test that limit of xn is equals to c. Okay, so where claim is xn tends to c as n tends to infinity. So since 0 less than mod xn minus c less than 1 by n for every n belongs to natural number, so Sandwich theorem tells you that limit of mod xn minus c is equals to 0. Now since limit of xn equals to 0 if and only if limit of mod xn equals to 0. So therefore this is true if and only if limit of xn minus c equals to 0. And then you can work out with the algebra of the sequences, okay, sum of the sequence and the difference of the sequences. Then you can show that limit of xn is nothing but c. Okay, so what you observe is once you have a real point, a point C is a cluster point of the given set A, then you will always be able to identify a sequence xn in A such that xn is not equals to c for every n and that limit of xn is c. And this is indeed that if and only if. So C be a cluster point of A if and only if you are able to extract a sequence in A satisfying this. Okay, right. So this also sometimes taken as a definition of for being a cluster point of a certain set A. Okay, right. So what is happening geometrically here? If you want to look at it, C be a cluster point. What you have decided, cluster point of A. So C may or may not be the part of that set A. Okay, so then you take, let's take, this is a point C. Okay, then you take a neighborhood, right, C minus 1 to C plus 1. Then let's take C minus half to C plus half and so on. So let's take this is C minus 1 by n to C plus 1 by n. So what is happening is C be a cluster point of A, then you will be always able to identify a sequence xn in A such that, so this here you can identify x1, this may be this side or this side, then another point that x2 will be here, then and so on, xn is getting closer to towards C as you goes n goes to infinity. Okay, right. Now, as told, this result here that a number C in R is a cluster point of a subset A of R if and only if there exists a sequence An in A such that limit of An equals to C and An not equals to C for all n belongs to natural number. So you can actually, for going converse, you can use the contradiction argument that suppose the C is not a cluster point but are able to identify a sequence. Okay, then try with it, and then if you are not able to get it, let me know. We will discuss it in the next session. Okay, the very first example is a finite set has no cluster point. Okay, so you take whatever the finite set, then none of the point is going to be a cluster point. Okay, so let's do with this. So let us consider. So we want to claim that finite set as no cluster point. Okay, so let A is equals to A1, A2, and so on, AN be a finite set. Okay, and these AIs are such that A1 less than A2 less than and so on less than A. Now let C belongs to R. Okay, so C may be any point, either it may belongs to A or it may not belongs to A, we don't know. Okay, right. Now claim C is not a cluster point of the set A. Okay, right. Now let and C is less than A1. Okay, then whether you are able to identify a neighborhood of C which does not contain any element of the set A. So I can decide, so if you look at the real line, so let's say this is A1, A2, A3, and so on. Let's say this is AI minus 1, some AI, this is AI plus 1, and so on. This is A. So by this condition, C is less than A. So you have C is here. Okay. Now what you can do is you can look at the distance of this A1 minus C by A1 minus C, and you choose, let's say, delta is equals to A1 minus C by 2. So then it's certainly positive, and B delta of C intersection with A minus C is empty. That can be shown. Okay, indeed, C is also not a part of A, so that is why, so minus C will not make any difference here. Okay, now on the other hand, if C is lying on the right, then you can choose for this case. So you have, let's say this is delta 1. Now then delta 2 is equals to C minus A n by 2, which is greater than 0, and V delta 2 of C intersection with A is empty set. So which says that if C is, lies outside A, okay, means if C is this side or that side, you will be always able to find a neighborhood such that which does not contain any point of A. Okay, right. Now suppose C lies anywhere between A1 to AN. So let's say C is somewhere here. Okay, let's say C is on between AI to AI plus 1. Okay, right. So what you can do here is, so here you will choose delta 3. So is equals to minimum of AI plus 1 minus C by 2 comma C minus AI by 2. Certainly it is going to be greater than 0, and that corresponding neighborhood of C will not contain the point of A. Now, suppose the point C is lies on the point A. So suppose C is equals to AI now. Okay, then what you will do is in this case, so for the case when C is equals to AI, then you can choose delta 4. This is equals to minimum of AI plus 1 minus AI by 2, comma AI minus 1 by 2. Then this delta 4 will work for the same. Okay, so here a C belongs to AI to AI plus 1, this interval. Okay. For this case, it was AN is less than C. In this case, C is less than A1, 2, and this is 3, and this is 4. So none of the case means it is C does not become a cluster point of the set. So therefore, the set has no cluster point. But that will never imply that every infinite set has a cluster point. Okay, so that does not, in this statement, a finite set has no cluster point does not imply that every infinite set has cluster point. So for example, you can look at the set of natural numbers. So let A is equals to set of natural numbers, okay, which is nothing but 1, comma 2, comma 3, and so on. Then you can show that A does not have cluster point. So you are going to follow the same argument. Okay, maybe so if C is less than A1, less than 1, then you have one case, and another case is C lies between any I to I plus 1. So you will discuss in a similar manner for this case as well. Okay, right. So for a point C belongs to the interval, let's say I to I plus 1, where I is a natural number. So then you have a delta I is equals to minimum of I plus 1 minus C by 2 at C minus I by 2. That delta I will work for this case. Okay, and then that neighborhood of C will not have any point of A. Okay, and that shows that A does not have the given, the natural number does not have any cluster point. Right. So next, let's consider the set A equals to the closed interval 0, 1 intersection with the set of rational numbers. Okay, and then we show that every point is a cluster point of the set. Okay, but if a point outside A will not be the cluster point of the set. Okay, now suppose let X belongs to R. Okay, such that X does not belongs to A, means outside this interval 0. Okay, then suppose you have two cases, right? One is X less than 0 or X is greater than 1. So you will again follow the similar argument for going to, for having the neighborhood in this case. So when you have this here, this case, what delta will work here is going to be, so 0 minus X by 2, that is going to be the length divided by 2, which is greater than 0. And for this case, the delta is equals to x minus 1 by 2 will work. Okay, so if outside A, none of the point is going to be the cluster point. Okay, now let's take the point which are rational numbers. Okay, so let x belongs to let x belongs to 0, 1 intersection with a set of irrational numbers. So x is an irrational number. Now we want to see whether this x is going to be a cluster point of A or not. Okay. Now to take any neighborhood of delta x. So this is going to be y in R such that mod of x minus y is less than that. Means you have all the possible points in R satisfying this for any delta. Okay, means this is equals to y in R such that x lies between y minus delta less than x less than y plus delta. Now since density theorem tells you that between every two real number there is always a rational number. Okay, so due to that argument, okay, so the density theorem, implies that V delta of x intersection with A minus singleton x is non-empty. So every irrational number which are the part of the closed 0, 1 is going to be the cluster point of A. Okay, right. Now let's talk about the points of A. Okay, now similarly you can talk about for the points x in A. So let x belongs to A, clause 0, 1 intersection with. So there are various cases now. So x equals to let's say first x equals to 0. Then you can create the sequence xn is equals to x plus 1 by n, which is not equals to 0, and limit of xn is equals to x, and the sequence xn belongs to the set. So this tells you that 0 is a cluster point of the set. Now case x equals to 1, you take the sequence xn is equals to x minus 1 by n, so that it lies inside the set A, which is not equals to 0 for not equals to 1 for every n in natural number, and limit of xn is equals to x, and limit xn is equals to x, and limit as xn equals to x, xn sequence is inside A. So this tells you that 1 is also a cluster point. Okay, right. Now when the case 0 less than x less than 1, yeah, so when so in the case 0 less than x less than 1, you consider any neighborhood of x. to consider any neighborhood of X, then density theorem tells you that that will always intersect with A and has contains at least one point of A other than X. Then density theorem again implies that every neighborhood contains at least one point of A other than X. Okay, right. Next, we are going to now position of defining the limit of function of single variable. Okay, so this is as follows. So let A is a subset of R and C is in R be a cluster point of A. For a function f from A to R, a real number L is said to be a limit of f at C if given any epsilon bigger than 0, there exists a delta positive such that if x belongs to A and x is such that 0 less than mod x minus c less than delta, then mod of f of x minus L is less than epsilon. So note that x is inside A, but C may or may not be the part of A. Okay. Therefore, f may or may have similar. Therefore, f also may or may not be defined on the point C, and hence here that is why here equal to sign is not there. Okay. So we have considered here the deleted neighborhood of C instead of the neighborhood of C. So in terms of mathematical form, the notation for deleted neighborhood of C with radius delta is B delta of C minus single. Means you are punctured at the point C and you consider rest of the points. Okay. So if you want to look at this in terms of neighborhood, this is as follows. So in other words, for every epsilon greater than 0, you will be always able to identify delta greater than 0, thus that f of x lies inside the neighborhood of L, epsilon neighborhood of L, whenever x is lies in the deleted neighborhood of C and x is in A. Okay, right. So if you look at it geometrically, what does it mean? Is we have considered that this is an epsilon neighborhood of L and this is the delta neighborhood of C. So for given epsilon neighborhood of L, you will be always able to identify a delta neighborhood of C. So which lies on y-axis and x-axis respectively. Okay, so for a given epsilon neighborhood of L, you will be always able to decide a delta neighborhood of C such that whenever you take any point, you pick up any point from the delta neighborhood of C, which is means like we are taking only the points which are the parts of A and punctured at C. So we are looking at only those points. Then for every point x in this, that given function f approaches towards L. Okay, so since there are only two directions for x for a given point x to approach C, so either from the left or from the right. Okay, so there you will you may also discuss with the concept for discuss the concept one-sided limits. Okay, right. So this curve is stands for here f of x. So f of x approaches to L as x approaches to C. So this is C for given epsilon. So that epsilon may be however large or this epsilon may be however small. Okay, so this epsilon may be chosen in this fashion. So you will always be able to identify a neighborhood of C satisfying this geometry. Okay, right. Once if you have noted that, once if you have confirmed that the limit x tends to c f exists, if limit x tends to c f of x exists, and that is equals to L, then we say that f converges to L at C. And in terms of notation, f, we are writing f tends to L as x tends to C. This is one of the abused notation you can say, because we have made the silent x here. So whether you write x or not doesn't matter here. Okay, so f of x tends to L as x tends to C. So whenever this limit exists, we say in other words that f tends to L as x tends to C, or f converges to L at C. Okay, so if limit does not exist, then we will say that f diverges at C. Okay, right. And now you want to say that f diverges at C. What does that mean? Means it is the negation of the definition. It's the negation of the definition. Now, if you read again what the definition, then you will certainly able to identify what will be the possible negation of it. So let me read the condition again. Given any epsilon, there exists a delta such that if x belongs to A and x lies inside the deleted neighborhood of C, then mod f of x minus L is less than epsilon. Okay, so what will be the possible negation of this statement? So if I want to write the negation of it, is as follows. So for given epsilon naught greater than 0, there does not exist delta greater than 0 such that this condition satisfied. Okay, means what will happen is, means that given epsilon naught bigger than 0, mod of f of x minus L is greater than equals to epsilon naught for all delta such that x belongs to B delta of C intersection with A minus singleton C. So this is going to be the negation of the result. That okay means you whatever delta you choose, the mod of f of x minus L is always going to be greater than equals to epsilon. Now this result will tells you about the uniqueness of the limit, and which is very much necessary. So like the sequence also, real sequences have unique limit. Okay, similarly if the function have limit, it is going to be unique. So in other words, if you say limit x tends to C f of x is equals to L1, and some other identify that limit x tends to C f of x equals to L2. So either there is some problem in the proof or limit does not exist. So if limit exists, then claim is L1 equals to L2. So we will also prove in the same way this result as we did in the case of uniqueness of limit for sequences. Okay, right. So let's prove it. So given f from A to R and C is a cluster point of A, and let L1 and L2 are two limits of the function at x equals to C. Okay, then we want to claim that L1 is equals to L2. Now we are going to first use the definition of limit. So for the first case, limit x tends to C f equals to L1. What the definition implies? This implies that let epsilon bigger than 0 be given. Then there exists delta 1 greater than 0 such that mod of f of x minus L1 less than epsilon by 2 whenever 0 less than mod x minus c less than delta. Means, so here we have created an artificial epsilon by 2 it is. Okay, so instead of this epsilon by 2, you can also work with epsilon, not a problem. Now, the second part is going to be as follows. So, limit x tends to c f equals to L2. So, for given epsilon, there exists delta 2 greater than 0 such that happen mod f of x minus L2 is less than epsilon by 2 whenever 0 less than mod x minus c less than delta. Now, we want to make these two conditions on the same delta. So, therefore, we will choose delta to be minimum of this delta 1 and delta 2. Then we can replace this delta 1 and delta 2 by delta. Okay, right. So, we choose define delta equals to minimum of delta 1 comma delta 2. Now, 0 less than equals to mod L1 minus L2. Now, add and subtract f of x. So, then use triangle inequality. And now, if you choose delta 1 comma delta 2, so you have taken x such that x belongs to the delta neighborhood of p, which is belongs to the this set. X belongs to the following set, where delta of c intersection with a minus. Then this quantity is going to be less than epsilon by 2, and also this quantity is also less than epsilon by 2 due to the previous. So in together, this is going to be epsilon. So we have started with an arbitrary epsilon, and we have ended with the 0 less than equals to mod L1 minus L2 less than epsilon. So therefore, this is true for every epsilon. So this only can happen whenever the mod of L1 minus L2 is equals to 0. So this is if at all if L1 equals to L. So this confirms that if the limit exists for a given function f, then it is unique. Okay, right. Now, the next result is the definition rewriting here. Okay, so we have already written this in the definition itself. Okay, so let f from A to R and let C be a cluster point of A, then the following statements are equivalent. So first implies 2 and 2 implies 1. This is what the meaning of equivalent. So limit x tends to c f of x is equals to R. L means the limit of f exists at x equals to c, or f converges at c. Then given any epsilon neighborhood of L, there exists a delta neighborhood of c such that if x not equals to c is any point in V delta of c intersection A, means x belongs to this set, then f of x belongs to the epsilon neighborhood of L. Okay, so means this is if and only if f of x belongs to the epsilon of L whenever x belongs to this set. So for given epsilon, there exists delta such that this happens. So this already has been discussed. Okay, right. So let's discuss about some of the examples. Okay, right. Now look at the first example. If you compare f of x is equals to b, L is equals to b, let epsilon bigger than 0 be given. Okay, now mod f of x minus L is equals to mod of b minus b, that is equals to 0, and which is certainly less than epsilon. Okay, for all x, right? And you can say whenever 0 less than mod x minus c less than delta. So you can choose delta equals to epsilon. So for a given epsilon, you can choose delta is delta equals to epsilon, or any delta will work here. Now, the next example, limit x tends to c, x equals to c. Okay, so if you compare here, f of x equals to x, L equals to c. And now find the difference of f of x minus L. Mod of f of x minus L equals to mod of x minus c, and which is certainly less than epsilon whenever you choose 0 less than mod x minus c less than delta, and delta if you choose equals to epsilon. If you choose delta equals to epsilon, you are through with this. So your objective is to create an artificial delta or artificial epsilon, whichever is easy for you. Okay, now look at the third example. Limit x tends to c, x square equals to c square. So if you compare f of x equals to x square and L equals to c square. Now compute the difference, their difference. So in magnitude, so magnitude of f of x minus L equals to magnitude of x square minus c square. That is equals to mod x minus c into mod x plus c. Now if you use that triangle inequality, this is going to be less than equals to mod x minus c times mod x plus mod c. Now we are going to bound this by a certain number. Now let mod x minus c is less than delta. Okay, then what about mod x? Okay, so that we are going to see. So let delta greater than 0 be such that mod x minus c is less than delta. So this is implies c minus delta less than x less than c plus delta. Now this implies mod x is equals to x minus mod of, you add and subtract x minus c plus c. Then use that triangle inequality. Okay, now use the triangle inequality. Now since mod x minus c is less than delta, so this is going to be less than equals to delta plus mod c. Now use this fact in the above inequality. Mod f of x minus L was less than equals to mod x minus c times mod x plus mod c. Now mod x is less than equals to delta plus mod c. So this implies this time mod x minus c is less than delta times delta plus 2 times mod c, because mod x is less than delta plus mod c. Delta plus mod c is delta plus 2 mod c. Okay, what we require is this is less than epsilon. So you just solve it out for which values of delta this inequality remains true. Okay, then you are done. Okay, so similarly you can go for the results for limit x tends to c, x to the power n equals to c to the power n whenever n belongs to natural number. Okay, right. Okay, now the very next result is again one of the other way for representing the definition of existence of limit, okay, for a given function f at x equals to c. So in some of the textbook this also will be taken as a definition. Okay, so let f from a to r and let c be a cluster point of a, then the following statements are equivalent. So limit exists for f at x equals to c, and which is equals to l. So for every sequence xn in a that converges to c such that xn not equals to c for all n within n. So this is always possible, right? Because c is a cluster point of a if and only if this condition satisfied. Then the sequence, if you take sequence of images of x, okay, that will give you a new sequence that is also going to be converges to n. If you take any sequence that converges to c such that xn is distinct from c for every n, then the sequence f of xn converges to n. Okay, so let's look at the proof. So let limit x tends to c, f of x equals to l exists. First implies 2. Okay, we are going to show first implies 2 first. Then we will show 2 implies 1. So let's call this as equation number 1. Now let's assume that xn be a sequence in A such that each xn is distinct from C for every n, and limit of xn equals to C. Then our claim is f of xn converges and limit f of xn is equals to f. Now, the first equation implies what? The definition of the limit. For given epsilon, there exists delta such that mod f of x minus L is less than epsilon whenever 0 less than mod x minus c less than L. Let's call it this number 3. Now, use the definition 2 here. Use the equation 2 here. That limit xn equals to c. So, for a given delta, there exists a stage afterwards x's are getting closer to c, okay, with distance delta. Okay, so means there exists a k in natural number such that 0 less than mod xn minus c less than delta for all n greater than equals to p. Let's call it as 4. Now we are going to use 3 and 4. Okay, now start with, let's say n is greater than equals to k. Okay, let n is greater than equals to k. Then this condition holds true, 0 less than mod xn minus c less than delta. Therefore, 3 implies what? What is that 3? Whenever 0 less than mod xn minus c less than delta, then mod of f of x minus L is less than epsilon. Okay, so therefore that implies mod of f of xn minus L is less than epsilon because xn satisfying this condition. Now, this implies what? This is true for all n greater than equals to k. Means what? If for a given epsilon, you are identifying a stage where f of xn is getting closer towards L. That means f of xn converges and limit of f of xn is L. So, one way is true. Now, conversely means second implies what? We are going to now look at this case. So let the following condition hold true. So for every sequence xn in A such that xn distinct from C, xn converges to C as n tends to infinity, then f of xn converges to L. Then we want to show that limit x tends to C, f of x is L. So we are going to use the contradiction. Okay, suppose that limit x tends to C, f of x is not equals to L. Then you are going to use the negation of the definition. And then you are going to expect a sequence in A satisfying this condition, but f of xn will not come. Okay, then our assumption was wrong, and then we have established our claim. Okay, so suppose that limit is not equals to L. Now, then for every delta there exists. So then for epsilon not bigger than 0, okay, such that this for there no matter what delta you choose, okay, for some epsilon not greater than 0, for every delta greater than 0 and for some epsilon not greater than 0, such that mod f of x minus L is greater than equals to epsilon naught whenever 0 less than mod x minus c less than. Now you create a sequence xn in A. For the same, what we are going to do is we are going to choose, because this is true for every delta greater than 0, so we are going to choose delta is equals to 1 by n. Then you choose xn in A satisfying this. So 0 less than mod xn minus c less than delta. Okay. Certainly xn is not equals to c because mod xn minus c is greater than 0, strictly greater than 0. And this above condition tells you that mod of f of xn minus L is greater than equals to epsilon naught, whatever n value will be. So this implies that f of xn not converges to L. Okay, right. So this implies that f of xn does not converge to L. But you are able to identify a sequence in A satisfying the property that xn converges to C as n tends to infinity. But f of xn does not converge to. So this is a contradiction to the given condition. So therefore, our assumption is wrong that limit x tends to C f of x is not equals to L. So hence, that is wrong. this implies that limit x tends to c f of x must be equals to L. Okay, right. Now, so final result here, that which is nothing but the negation of the above result. Okay, means if f does not have a limit L at C, then if and only if. Okay, so if L belongs to R, then f does not have limit L at C. If and only if you are able to identify a sequence xn in A, where each xn is distinct from C, and xn converges to C, but the sequence of its images xn does not converge to L. If you are able to satisfy this condition, then you can guarantee that f does not have limit L. Maybe some other limit, but if it is f of xn does not converge to L, then it will certainly does not have limit L. So the second result says that the function f does not have limit at C if and only if there exists a sequence xn in A where each xn is distinct from C, and xn the limit is C, but the sequence f of xn does not converge in R, means it diverges. So if f of xn diverges, means it does not have limit at C, means the limit does not exist. Now, how to utilize these results? Then we are going to look at some examples. Okay, right. So the very first example is limit x tends to 0, 1 by x does not exist in R. Okay, so either you try to establish the negation of the above result of the definition, okay, or you try to identify a sequence, okay, in the neighborhood of 0, because see x tends to C, means C is 0, so we are looking in the neighborhood of 0. You know, if you compare f of x is 1 by x, it is defined everywhere except at 0, right? So you try to see in the neighborhood of 0 and try to find a sequence in that neighborhood which is converges to 0, but whose image is not converges, then it is you are true. So for doing this, I'm going to create a sequence xn which is very familiar to us, that is going to be 1 by n. Instead of this, you can go with 1 by n square or and so on. So certainly xn is not equals to 0 for every n, and limit of xn is 0. Now, what is f of xn? Is equals to 1 by xn, that is going to be n. And you know that the sequence f of xn, that is sequence of n, means 1, 2, 3, 4, that diverges, does not converge, diverges in R. So this certainly implies that limit x tends to 0, 1 by x does not exist in R. Now, for second, you know what is the signum function? Is defined as is equals to mod x by x whenever x is not equals to 0, and 0 whenever x equals to 0. Now for this case, again we will follow the same approach, that you decide the sequence xn is going to be minus 1 to the power n by n to the power p, where p is greater than 1, or you can, greater than 1. Then limit of xn is 0. Moreover, xn is not equals to 0 for every n. And what is the signum function of xn? Is, you can look at the sequence signum of xn, that is going to be nothing but signum of xn is equals to minus 1 to the power n, and which is oscillating sequence which also diverges in R. Okay, and hence limit x tends to 0, signal function x does not exist. For the third limit x tends to 0, sine of 1 by x does not exist in R. Again, you will create an artificial sequence, okay, which converges to 0, but sine of 1 by x does not converge. So again, you know that sine of odd multiple of pi by 2 is minus 1 to the power n, is oscillating. So you try with that. So we are creating xn is equals to 2 by 2n minus 1 pi. So that 1 by xn is going to be odd multiple of pi by 2, and which is certainly not equal for odd. Further, limit of xn is 0. Okay, and f of xn is equals to sine of 2n minus 1 pi by 2, that is going to be minus 1 to the power n minus 1. So for n belongs to natural number. Right? So, but that sequence f of xn does not converge. Therefore, the limit, this implies limit x tends to 0, sine of 1 by x does not exist. 1 by x does not exist. Okay? Yeah. So we are closing here. Okay? Fine. Thank you.